Hello and welcome to Earthly Teachings, where learning is clear and powerful. Today, we are working on Mathematics N6. Specifically, we'll be tackling Unit 5.2, Calculating Area. By the end of this video, you will be able to, first, use definite integrals to calculate the area of a region bounded by one or more curves. Second, you'll be able to skillfully choose between vertical or horizontal strips to simplify your calculations. And third, you'll gain the confidence to handle the algebra required for these problems, including finding points of intersection and making variables the subject of an equation. Let's learn together. Our journey begins by revisiting a core concept you may have encountered in N5, calculating bounded areas. Remember, the fundamental idea is to take a complex shape and divide it into a large number of very thin, simple shapes, which we call representative strips. The definite integral is nothing more than the sum of the areas of an infinite number of these incredibly thin strips. We follow a straightforward two-step procedure. Step 1. Always start by sketching the graphs. This visual representation is crucial for understanding the problem. Once you have your sketch, clearly identify the specific area you need to calculate. Step 2. Choose the representative strip that will simplify your calculation the most. This is often the key decision. Once chosen, you can apply the appropriate area formula. So step 1 is to draw it, and step 2 is to choose the best way to slice it. Let's formalize those ideas into the two main formulas we will be using, depending on whether we choose a vertical or a horizontal strip. First, the vertical strip. Imagine slicing your area with very thin vertical rectangles, each of width. The area of each strip is its height times its width. The trick is to find the height in terms of x. If the upper end of your strip touches a curve y and the lower end touches the x-axis, the height is just y. The formula for the total area is the integral from a to b of y dx. More often, the area is bounded between two curves, say y1 and y2. In this case, the height of our vertical strip is the difference between the y value of the top curve and the y value of the bottom curve. So we integrate y1 minus y2 with respect to x from the leftmost x value a to the rightmost x value b. A helpful memory tip is to use subscripts. Let y sub t be the top curve and y sub b be the bottom curve. So our formula becomes the integral from a to b of the top curve minus the bottom curve with respect to x. Again, this means integrating the height of the strip y top minus y bottom from the starting x point a to the ending x point b. Now, let's look at the second option, the horizontal strip. This time, we slice the area with very thin horizontal rectangles, each of width d. The area of each strip is its length times its width. Here the length is an x value, which must be expressed in terms of y. If the right end of your strip touches a curve x and the left end touches the y-axis, the length is x. The formula for the total area is the integral from a to b of x dr. Just like before, the area can be bounded between two curves, say x1 and x2. When integrating horizontally, the length of the strip is the right curve minus the left curve. We integrate x1 minus x2 with respect to y from the lowest y value c to the highest y value d. Using subscripts again, let's call the rightmost curve x sub r and the leftmost curve x sub l. Our horizontal strip formula becomes the integral from c to d of the right curve minus the left curve with respect to y. It's the same logic. We integrate the length of the strip, right minus left, from the starting y point c to the ending y point d. Understanding why we use these formulas is the key to mastering this topic. It's all about summing up an infinite number of very thin rectangles. Before we dive into the examples, we need to master a crucial skill: rewriting equations. You see, for vertical strips, we need the equations in the form y equals f of x. For horizontal strips, we need them in the form x equals g of y. Let's work through the examples one by one. First, the equation of a circle. X squared plus y squared equals 9. To express e in terms of x, we isolate y. Subtract x squared from both sides, then take the square root. Remember to include the plus or minus sign, as there are two y values for each x, the top half and the bottom half of the circle. To express x in terms of y, we do the same, but isolate x. We get x equals plus or minus the square root of 9 minus y squared. Next, the hyperbola. x squared over 9 minus y squared over 4 equals 1. Let's find y in terms of x first. We need to get y alone on one side. We add y squared over 4 to the right and subtract 1. Combine the x terms with a common denominator. Then multiply both sides by 4 and take the square root. Don't forget the plus or minus. Simplifying the square root of 4 over 9 gives us 2, 3. Now for x in terms of y. The process is very similar. Add y squared over 4 to both sides, combine terms, multiply by 9, and take the square root. This gives us x equals plus or minus 3 over 2 times the square root of y squared plus 4. Next, let's look at exponential and logarithmic functions. For y equals e to the x, we already have y in terms of x. To find x in terms of y, we take the natural logarithm of both sides. This gives us x equals the natural log of y. Similarly, for y equals the natural log of x, we again have y in terms of x. To get x in terms of y, we use the definition of a logarithm. The base e raised to the power of the answer y equals the input x. So x equals e to the y. For the equation y equals 2 natural log of x, we first divide by 2 to get y over 2 equals natural log of x. Then, using the same logarithmic definition as before, we find that x equals e to the power of I over 2. For the simple hyperbola xy equals 6, finding both forms is easy. Divide by x for the y form and divide by y for the x form. Let's continue with the next set of equations. For y equals x to the 1/3, which is the same as the cube root of x, we already have the y form. To find the x form, we cube both sides, which gives us x equals y cubed. Next is y equals x squared. This is a parabola opening upwards. We have the y form. To find the x form, we take the square root of both sides, giving us x equals plus or minus the square root of y. Again, the plus or minus is important. Equation 9 is x equals y squared. This is a parabola opening to the right. We already have the x form. Taking the square root gives us the y form. Y equals plus or minus the square root of x. Now for a linear equation, 4x plus 3y plus 3 equals 0. For the y form, we solve for y by subtracting 4x and 3, then dividing by 3. For the x form, we solve for x by subtracting 3y and 3, then dividing by 4. We have two more equations to rewrite. For y equals x minus 1 all squared, the y form is given. To find the x form, we take the square root of both sides, giving us plus or minus the square root of y equals x minus 1. Then we add 1 to both sides, which gives x equals 1 plus or minus the square root of y. Finally, y equals 6 minus x squared. The y form is given. To find the x form, we need to solve for x. This is a quadratic equation, so the best method is to complete the square. First, multiply by -1 to make the x squared term positive. Then rearrange and complete the square on the x terms by adding and subtracting 9. This gives us x minus 3 all squared equals 9 minus y. Taking the square root and adding 3 gives us x equals 3 plus or minus the square root of 9 minus y. Notice that making x the subject here was quite involved. The original document makes a crucial point. From equation 12, it's clear that making x the subject is more involved, so we avoid it. This is an exam writing strategy. Choosing the right integration variable can save you a lot of time and effort. This brings us perfectly to our main task, calculating area. We are now ready to tackle the main problems. For each of the following, we must sketch the graphs, identify the area, show the suitable representative strip, and calculate the area. This follows our two-step procedure. Let's begin with our first problem. Find the area bounded by the circle x squared plus y squared equals 6, the parabola x equals y squared, and the line y equals 0 in the first quadrant. Step 1. Sketch the graphs and identify the area. We have a circle centered at the origin with radius the square root of 6, which is about 2.45. We have a parabola x equals y squared, which opens to the right. And we have the x-axis, y equals 0. To find the points of intersection, we can substitute the equation for x from the parabola into the circle's equation. This gives us x squared plus x equals 6, which is a quadratic equation. Rearranging it, we get x squared plus x minus 6 equals 0. We can factor this into x plus 3 times x minus 2 equals 0, giving two possible solutions for x equals -3 or x equals 2. For the first solution, x equals -3. The equation of the parabola is x equals y squared. So, -3 equals y squared. This has no real solution for y. Remember, we are working in the real number plane. This point is not valid for our area. For the second solution, x equals 2. Again, using the parabola equation, 2 equals y squared. This gives us y equals plus or minus the square root of 2. So the intersection points are 2 root 2 and 2 minus root 2. Now let's sketch it. We are interested in the area in the first quadrant, bounded by the parabola x equals y squared, the circle x squared plus y squared equals 6, and the x-axis y equals 0. The graph looks like this. The shaded area is the one we need to calculate. Notice the intersection point in the first quadrant is 2 root 2. Now for step 2. Choose the strip and integrate. This is where the magic happens. Let's consider our options, vertical or horizontal strips. If we use a vertical strip, notice the bottom curve is always the x-axis, y equals 0. But the top curve changes. On the left, it's the parabola y equals the square root of x. On the right, it's the circle y equals the square root of 6 minus x squared. This means we would need two separate integrals. That's a lot of extra work. Now, let's look at a horizontal strip. Notice the rightmost curve is always the circle, and the leftmost curve is always the parabola. This is perfect. The top and bottom curves are the same across the entire area. We can calculate this area with just one integral. So, we choose the horizontal strip. Since we are using a horizontal strip, we must express the equations in terms of y. The circle equation x squared plus y squared equals 6 becomes x equals the square root of 6 minus y squared in the first quadrant. The parabola is already in the correct form. X equals y squared. Our formula is a equals the integral from c to d of x right minus x left with respect to y. The bottom limit c is the lowest y value of our area, which is at the origin y equals 0. The top limit d is the highest y value, which is at our intersection point. y equals the square root of 2. Substituting everything, our integral is the area A equals the integral from 0 to root 2 of the square root of 6 minus y squared with respect to y. Now we need to integrate this. We have the integral of root 6 minus y squared and the integral of y squared. The integral of y squared is straightforward. The integral of the square root term requires a special formula. This is a common integral to know, but is often provided in formula sheets. The formula for the integral of the square root of a squared minus b squared x squared is a over 2b times sine inverse of bx over a plus x over 2 times the square root of a squared minus b squared x squared. Let's apply this to our first term, using y instead of x. Our term is the square root of 6 minus y squared. Comparing this to the formula, we see that a is the square root of 6 and b is 1. Plugging these values in gives us the antiderivative for the square root term. The antiderivative for y squared is simply y cubed over 3. Now we can write down our full antiderivative and evaluate it at the limits of integration, root 2 and 0. First, we plug in the top limit, y equals root 2. Then we plug in the bottom limit, y equals 0, and subtract the second result from the first. Notice that when we plug in the lower limit of 0, every term becomes 0, except for the sine inverse term, but sine inverse of 0 is also 0. So we only need to evaluate at the upper limit. Before using a calculator, notice that the square root of 2 over the square root of 6 simplifies to 1 over the square root of 3. Also, root 2 squared is 2. Let's simplify the expression. We have root 6 over 2 times the sine inverse of 1 over root 3. The square root of 4 is 2, and root 2 times 2 is 2 root 2. And root 2 cubed is 2 root 2. The sine inverse of 1 over root 3 is approximately 0.615 radians. We can see that root 2 minus 2 root 2 over 3 is 1 over 3 times root 2. Now we need to use a calculator. It is absolutely crucial that your calculator is in radian mode. Plugging everything in, we get an area of approximately 2.318 square units. The memo in the document gives the same answer. That's a good sign we're on the right track. On to our next problem. Find the area bounded by the parabolas x equals 4 minus y squared and x equals y squared, and the y-axis, x equals 0, in the first quadrant. Step 1. Sketch and identify. The first equation, x equals 4 minus y squared, is a parabola opening to the left. The second, x equals y squared, is a parabola opening to the right. The third, x equals 0, is just the y-axis. To find the intersection of the two parabolas, we set them equal to each other. I squared equals 4 minus e squared. Add y squared to both sides to get 2y squared equals 4, so y squared equals 2. This gives y equals plus or minus the square root of 2. Substituting back into x equals y squared, we get x equals 2. So the intersection points are 2, root 2. And 2 minus root 2. We are interested in the area in the first quadrant, bounded by these three curves. A sketch is essential to see what this region looks like. This graph shows the two parabolas and the y-axis. The shaded region is the one we need. The intersection point in the first quadrant is 2 root 2. Step 2. Choose the strip and integrate. Let's use a vertical strip first to see if it works. The bottom curve, y sub b, is always the x-axis, y equals 0. But the top curve, y sub t, changes. It's the parabola y equals root x on the left and y equals root 4 minus x on the right. Just like our previous problem, this would require two separate integrals. Now let's try a horizontal strip. The leftmost boundary is always the y-axis, x equals 0. The rightmost boundary is always the parabola x equals 4 minus y squared. This is a single continuous boundary. So, a horizontal strip is the best choice here. The original problem and its solution in your document actually used a vertical strip for this problem and got the correct answer. This shows there can be more than one way to solve a problem. Let's follow their method to show you how it's done, but remember, the horizontal strip method would have been simpler here. Using the vertical strip, we have to split the area into two parts. Area 1 goes from x equals 0 to x equals 2, and is bounded by y equals root x on top and the x-axis on bottom. Area 2 goes from x equals 2 to x equals 4, and is bounded by y equals root 4 minus x on top. Total area A equals A1 plus A2. Let's calculate area 1 and area 2 separately and then add them up. Area 1 is the integral from 0 to 2 of x to the 1/2 dx. The antiderivative is x to the 3/2 divided by 3/2. Evaluating this from 0 to 2 gives us 2 times 2 to the 3/2, all over 3. Now for area 2. Area 2 is the integral from 2 to 4 of 4 minus x to the 1/2 dx. The antiderivative is 4 minus x to the 3/2, divided by 3/2, and multiplied by -1 because of the chain rule. Evaluating from 2 to 4 gives us 8 over 3 minus 2 over 3 times 2 to the 3/2. Finally, we add the two areas together. The total area is 4 root 2 over 3 plus 4 root 2 over 3, which equals 8 root 2 over 3. This is approximately 3.771 square units. Now let's compare this to the document's solution. Their answer is 1.562. There's a big difference. Let's find out why. The document's solution integrates from 0 to 2, the top curve minus the bottom curve, with respect to x. Let's trace this area. This integral calculates the area of a vertical strip from y equals root x down to y equals root 4 minus x. If we shade this region, we see it is the exact same area as the one bounded by x equals 4 minus y squared, x equals 0, and y equals root x. In other words, they are calculating the area of the region bounded by x equals 4 minus y squared, x equals y squared, and the x-axis in the first quadrant, but only integrating one part of it. The document's calculation is for a different area than the one described in the problem. The problem asked for the area between the two parabolas and the y-axis, which is the region we first identified as being simpler to integrate with a horizontal strip. Let's recalculate the area of the document's problem, which is integral from 0 to 2 of root 4 minus x minus root x dx. Splitting it up gives us the integral of root 4 minus x minus the integral of root x. Evaluating the first integral from 0 to 2 gives 8 root 2 over 3 minus 8 over 3. The second integral we already know is 4 root 2 over 3. Subtracting these gives 4 root 2 over 3 minus 8 over 3, which is 1.562. The document's arithmetic was correct, but the area it calculated was incorrect for the problem statement. This highlights a critical point. Always double-check that your integral setup perfectly matches the shaded region you want to find. A tiny mistake in the limits or the integrands can lead to a completely different result. Let's move on to our third example. Here, we need to find the area between the line y equals 6 minus x and the hyperbola y equals 8 over x. Step 1. Find the points of intersection. We set the two expressions for y equal to each other. Multiply by x to clear the fraction. Rearrange into a quadratic equation. This factors nicely into x minus 4 times x minus 2 equals 0, so x equals 4 or x equals 2. Now find the corresponding y values by plugging these x values back into either original equation. When x is 4, y is 8 divided by 4, which is 2. So the point is 4, 2. When x is 2, y is 8 divided by 2, which is 4. So the point is 2, 4. Let's sketch the region. The hyperbola I equals 8 over x is in the first quadrant. The line y equals 6 minus x has a y-intercept of 6 and an x-intercept of 6. The bounded area is between the line and the hyperbola, between x equals 2 and x equals 4. Step 2. Choose the strip. In this case, a vertical strip is perfect. The line y equals 6 minus x is always the top curve, and the hyperbola y equals 8 over x is always the bottom curve. We integrate the top curve minus the bottom curve. This will be the integral from x equals 2 to x equals 4 of 6 minus x minus 8 over x, all with respect to x. Now let's find the antiderivative. The antiderivative of 6 is 6x. The antiderivative of x is x squared over 2. The antiderivative of 8 over x is 8 times the natural log of the absolute value of x. We evaluate this from 2 to 4. Remember, the natural log of x is only defined for x greater than 0, which our limits satisfy, so we can drop the absolute value. Let's plug in the limits. We plug in 4, and then plug in 2 and subtract. Let's simplify inside the brackets first. 24 minus 8 is 16. 12 minus 2 is 10. We get 16 minus 8 log 4 minus 10 minus 8 log 2. Now we combine the constant terms and the log terms. 16 minus 10 is 6. We have negative 8 times log 4 plus 8 times log 2. Using the logarithm property that the natural log of a minus the natural log of b is the natural log of a over b, this simplifies to 6 minus 8 times the natural log of 2. Calculating this gives us approximately 0.455 square units. The document shows a second method for this same problem using a horizontal strip. Let's see if we get the same answer. The intersection points are 2, 4, and 4, 2. The lowest y value is 2, and the highest is 4. These will be our limits. We need to rewrite our equations in terms of y. The line y equals 6 minus x becomes x equals 6 minus y. The hyperbola I equals 8 over x becomes x equals 8 over y. We can see from the graph that for any horizontal strip, the line x equals 6 minus y is on the right, and the hyperbola x equals 8 over y is on the left. So, our integral is the integral from y equals 2 to y equals 4 of 6 minus y minus 8 over y, all with respect to y. This is exactly the same integral as before, just with y instead of x. As expected, the antiderivative is the same, and when we evaluate it from 2 to 4, we get the identical result. 6 minus 8 log 2, which is approximately 0.455. This confirms our answer and shows that with some functions, both methods can be equally straightforward. This is a great way to check your work in an exam. Let's tackle our fourth example. Find the area between the two parabolas y equals x squared minus 6x plus 9 and y equals 6x minus x squared. Step 1. Find the points of intersection and sketch the graphs. Set the equations equal to each other. Rearranging gives us the quadratic equation 2x squared minus 12x plus 9 equals 0. This doesn't factor easily, so we use the quadratic formula. After some calculation, we find that x equals 3 plus or minus the square root of 6 over 2, which is approximately 5.49 and 0.551. Now let's sketch these parabolas. The first equation, y equals x minus 3 squared, is an upward opening parabola with its vertex at 3, 0. The second, y equals 6x minus x squared, is a downward opening parabola with roots at 0 and 6 and a vertex at 3, 9. The shaded area is between these two curves. Step 2. Choose the strip. A vertical strip is clearly the best choice here. The downward opening parabola is always on top, and the upward opening parabola is always on the bottom. The horizontal strip method would be much more difficult, as you saw in our early example of rewriting the equation. We'll use a vertical strip and integrate from the leftmost intersection point. X equals 3 minus root 6 to the rightmost point. X equals 3 plus root 6. The top curve is y equals 6x minus x squared, and the bottom curve is y equals x squared minus 6x plus 9. Our integral is the integral from 3 minus root 6 to 3 plus root 6 of the top curve minus the bottom curve. Let's simplify the expression inside the integral. Distributing the negative sign and combining like terms gives us 12x minus 2x squared minus 9. Now we find the antiderivative. The antiderivative is negative 2 to the 3x cubed plus 6s squared minus 9x. We need to evaluate this at our two limits. Plugging in these values can be a bit messy, so it's best to use a calculator. The document solution gives the limits as 0.879 and 5.121, which are different from our calculated roots. Let's recalculate the roots to be precise. The roots are 12 plus or minus the square root of 72 over 4. This is 3 plus or minus 3 root 2 over 2, which are approximately 5.121 and 0.879. The document's roots are correct. So the integral becomes, we evaluate the antiderivative from 0.879 to 5.121. The result is approximately 25.456 square units. The document's answer matches our calculation. Our final example involves exponential functions. Part 1 asks for the area bounded by y equals 2 to the x, y equals 2 to the negative x, and the line x equals 2. Let's sketch the curves. The function y equals 2 to the x is an exponential growth curve. The function y equals 2 to the negative x is an exponential decay curve. Both curves pass through the point 0, 1. Here is the sketch. We are finding the area between the two curves from the y-axis, x equals 0, all the way to the vertical line x equals 2. Step 2. Choose the strip. A vertical strip works perfectly here. From x equals 0 to x equals 2, the curve y equals 2 to the x is always on top, and y equals 2 to the negative x is always on the bottom. So, our integral is the integral from 0 to 2 of 2 to the x minus 2 to the negative x dx. To integrate an exponential function a to the x, the formula is a to the x over the natural log of a. So, the antiderivative of 2 to the x is 2 to the x over the natural log of 2. For the second term, we also divide by the natural log of 2, and due to the chain rule, we also divide by negative 1 from the exponent negative x. This simplifies to 1 over the natural log of 2 times 2 to the x plus 2 to the negative x, evaluated from 0 to 2. Now we evaluate at the limits. Plug in x equals 2, then plug in x equals 0. Simplify. Remember that anything to the power of 0 is 1. The natural log of 2 is approximately 0.693. Calculating the expression gives us an area of about 3.246 square units. Now for part 2. Calculate the area bounded by the same two exponential curves, but this time by the horizontal line y equals 2. First, let's find the points of intersection to determine our limits. For the intersection of y equals 2 to the x and y equals 2, taking the natural log of both sides gives x times log 2 equals log 2. So x equals 1. For the intersection of y equals 2 to the negative x and y equals 2, we find x equals negative 1. This area lies between x equals negative 1 and x equals 1. A sketch clearly shows that the top boundary is always the line y equals 2. However, the bottom boundary is not continuous. On the left, it's the decay curve, and on the right, it's the growth curve. This would require two vertical integrals. But look at a horizontal strip. The top is y equals 2, and the bottom is y equals 1. The right boundary is always the growth curve, and the left boundary is always the decay curve. A horizontal strip is the perfect choice for this problem. Since we're using horizontal strips, we must rewrite our equations for x in terms of y. We already did this in our first example. From y equals 2 to the x, we get x equals natural log of y over natural log of 2. From y equals 2 to the negative x, we get x equals negative natural log of y over natural log of 2. Our integral is from y equals 1 to y equals 2 of x right minus x left. Notice that subtracting a negative becomes a positive, so the area is the integral of 2 times log y, all over log 2. We need the antiderivative of natural log of y. This is a common result from integration by parts. The integral of natural log of yd is y times log e minus y. Plugging this in and evaluating at our limits gives us approximately 1.155 square units. Let's quickly recap what we've learned. First, the two-step procedure is always the best strategy. Sketch the area first and then choose your strip. Second, understanding why we choose a particular strip is key. If the top and bottom boundaries of a vertical strip are constant, choose vertical. If the right and left boundaries of a horizontal strip are constant, choose horizontal. This often avoids splitting the problem into multiple integrals. Third, the algebra is a significant part of these problems. You must be comfortable finding points of intersection, solving equations for x in terms of y, and using trigonometric or exponential identities. The more you practice these problems, the more intuitive the process will become. Remember to double-check your limits of integration and your algebraic simplifications. Thank you for watching. Like, subscribe, and continue learning with Earthly Teachings. Here's your call to subscribe animation.